So we're going to continue on here. And again, we're talking about last time really, or at least we finished up there with significant figures. So remember that when we do take a measurement, there's always some degree of uncertainty in that measurement. And when we do an actual measurement, we always want to record really all the certain numbers. So again, when you take that measurement, there really should be numbers that pretty much no matter who takes a look at it, everybody should agree. For example, hey, everybody should agree it's at least 4 or something. Now, there's also always a number that perhaps, if I looked at it, maybe I may go, well, I think it's sort of between two markings, like maybe halfway between. And I may call that, maybe like a 5 or something like that. Somebody else may look at the same sort of marking and go, well, no, I think it's a little further than halfway. And again, they may call it 6 or 7 or something like that when they do that. So it's always a custom when we are making measurements and taking measurements to record all those certain numbers plus the first uncertain number. And really when we do that in a measurement, that's basically what consists of significant figures. And it does vary, as we talked about, I think last time, that you really do want to make sure that you take a look at the actual scale on the piece of equipment that you're using, figure out really, for the most part, what the smallest marking represents. There's usually big markings on sort of the scales. There's small markings. And for the most part, not 100% of the time, but most of the time, you could take your reading to one more place to the right of the smallest marking. So for example, if the smallest marking was 0.1 of a centimeter, or 0.1 centimeters, you typically could take your reading to the second decimal place. If the smallest marking on a piece of equipment was like a whole number, like 1, or if it goes by 1 milliliter, for example, you typically could go one more place to the right and take that reading. We also talked about at the end there sort of the rules for counting significant figures. And the first one is pretty much that any non-zero is going to be significant. Remember, that's sort of where we always want to kind of start counting. We want to look at a number and really start on the left-hand side there and go left to right. And as soon as you hit that very first non-zero, that really is where you should start counting your significant figures. So again, anyone that's obviously not a 0 will be significant. Now, we also have zeros and several different types of zeros that we come across in a calculation or number. The first type of 0 are basically all the zeros that come before the first non-zero number, and those are sometimes referred to as leading zeros, and those guys are not significant. So again, if we had 0.000111, all these numbers here, zeros, would not be significant. We would start counting up that very first one, and this particular number here would have 3 significant figures. We then have zeros that are, again, what are referred to as sometimes being trapped zeros, captive zeros. They're basically zeros between non-zero numbers. And those guys are significant. So in this case, we actually would start counting up to 3 here. This 0 in the middle is trapped, so it would be significant. And the 3 at the end would also be significant. And this guy would have 3 significant figures in this particular case. And then we get the zeros that really come at the end. And as it says on here, and as we talked about last time, they may be significant, they may not be significant, but it really is what it says here, for example. Actually, no, I guess not, but there needs to be a decimal place in the number to be significant. And as we talked about, I think last time as well, again, the decimal point does not need to be like right next to those zeros. It just needs to be somewhere in the number. So for example, if you had 1.000, we would start counting here at the 1. All these zeros are what are referred to as trailing zeros. They come at the end of the number here, and they would be significant because there is a decimal point here in the number, and this guy would have 4 significant figures in that case. Again, if you wrote something like 100, just like that, technically speaking, no decimal written, the 1 would be significant. And again, here, these zeros at the end would not be significant because there's no decimal point in there, and this guy would have 1 significant figure. We also talked about, I think, the importance of the significant figures. It really does sort of tell us, how good or bad of a measurement, for example, that we made. If you're comparing, 100, for example, like that, 100 like this, or just 100 written like this. And if we assume all three of these guys were really measurements, right? We can look at the significant figures. This guy would have 4 significant figures. This guy would have 3 significant figures. And this guy would actually only have 1 significant figure. Now, when we talk about recording all the certain numbers and that first uncertain number, when we take a measurement, the idea here is just that the uncertain measurement or the uncertain value, or again, sometimes referred to as the estimated digit, that is not necessarily always the last digit that's written, but it is the last significant figure. So what that means is when we look at the first one here, that would be where the estimated digit would be. When we look at the second one, actually, that would be where the estimated digit would be. And when we look at the third measurement, that actually would be the estimated digit. And again, you can see not always the last number. And there is a big difference in sort of the quality of your measurement, depending on which one here. Again, everybody may look at this and go, hey, it's just 100, right? So it's all the same. It's really not, because remember, the uncertainty lies here, for example, in this guy, which means it could be something like 100.1. Maybe it's 100 even, or maybe it's like 99.9. That's a much smaller room for error in your measurement than if we just take the last measurement, where the uncertainty actually is in that first number, where we could say we think it's 100, but maybe it's actually as big as 200, maybe it's as small as like 0, basically. So, there's a very big range of error in this measurement. This guy over here, this measurement would be a much worse measurement than this one. This is a much better measurement, a lot lower room for error, a lot less room for uncertainty. And again, I think we talked it also in the context of, we never want to sort of lop off numbers, especially when we're taking measurements, because without realizing what we're doing is making a measurement really a lot worse than it should be. Any questions on that stuff that we talked about there last time? All right, so again, looking at these here, this would be 1 significant figure. Again, when we look at this number, there's no decimal point written, which means that 2 is really our only significant figure. It's also where our uncertainty is. So again, not as good a measurement as this guy. This guy actually has 4 significant figures, starting to count at the 4. All 3 of these zeros would be significant, again, because there is a decimal place in this particular number. Looking at a few other examples here, some of these zeros that we talked about, again, counting left to right, we would start counting here at the 4. The next one is a 4, which would be significant. And now this 0 at the end is going to be significant because there is a decimal point there, and that does give us 3 significant figures. These are leading zeros, which are not significant. Again, we would not start counting on the next one until we hit the 2. And we got 2 and 2, which gives us 2 significant figures. Same thing here. These are really all leading zeros. And again, we wouldn't start counting until we get to that 3. And that means there's only 1 significant figure. Any questions on those guys there? Now, again, although we normally think that, by default, there's a decimal point written, in the case of significant figures, if there is not a decimal point actually written in the number, then you should not assume that it is there. And again, because that would give you the wrong number of significant figures. So here again, we got the 4s, which are significant. All 3 of these zeros would be not significant because there's no decimal point, which again is why we got 2 significant figures. Same thing here, starting to count at the 8, and the 1 is significant, 0 at the end, not significant. And here, these 3 are significant, these zeros at the end are not significant. And again, they're really just to hold the meaning of the number. Really, they're not really measured. And the uncertainty now, if we were asked what the uncertain digit is, the estimated digit, they would be the 4 in this case, because that's the last significant figure. It would be the 1 in this case, because that's the last significant figure. And it would be the 5 in this case, because that's the last significant figure. So this is a good illustration. I was just talking about that. Sometimes you're asked, what is the estimated digit? And people sort of almost automatically go, should be the last number written. But again, should not always be the last number. It is the last significant figure that's there. Any questions on that there? Yeah. So we took some time earlier and talked about scientific notation. And just a reminder that in general, right, as we talked about, proper scientific notation has this general form of 10 times n to the n, where the first n, again, is our number between 1 and 10. This is either positive or negative, depending on which way you move. But one of the important things, again, in terms of significant figures in scientific notation is all of the numbers that come before the times 10 part of the number are significant. So if we look at this guy written in scientific notation, all 3 of these numbers are significant. We look at this one, these are all the numbers that come before the times 10 part. They're significant, which would be 2. And here that is like 5, if I'm counting that right, would be significant here. The nice thing about sort of scientific notation and significant figures is there are some cases where, when you do a calculation, for example, and hey, this answer should end up with a certain number of significant figures, there's sometimes only one way to get to the right number of significant figures, and that is to write the number in scientific notation. So for example, if we were dealing with a number like, 1.25 times 10 to the 2, for example. All right, if I wrote it like this would be 3 significant figures. But let's just say I did the calculation and I needed 2 significant figures. I could do that very easily by just going 1.3 times 10 to the 2. Now this has 2 significant figures. If I needed 1 significant figure, I could simply just go 1 times 10 to the 2. Now I have 1 significant figure. So because in scientific notation, you can kind of control how many significant figures you write for an answer. It's sometimes, like I just mentioned, is the only way to get yourself to the right number of significant figures. Any questions on that there? Which brings up a really good point of when we go from sort of what's sometimes referred to as positional notation, which is like a regular number, to scientific notation, we should always maintain the same number of significant figures. So when we look at our original number here of 500, we do see the decimal point written, which implies that these zeros at the end are significant, and this number has 3 significant figures. Again, when we go 2 places to the left, that now should have also 3 significant figures. We would not want to write this one as 5 times 10 to the 2, because that would now have only 1 significant figure, and we would have lost some significant figures along the way. So it's really important that as you go from sort of positional notation to scientific notation, you do maintain the proper number of significant figures. And that's what we see when we look at this number. Again, all those zeros at the end are not significant. The only significant number there is the 4, which means when we turn it into scientific notation, that is why we dropped all those zeros. Because if I kept all those zeros, I now would have too many significant figures. So you never should add more significant figures or lose significant figures as you go from regular number to scientific notation back and forth. You do need to maintain the same number of significant figures there. Same thing here. This actually, again, has two significant figures. The original number, the 0, is significant. So when we bring it into scientific notation, we keep the two significant figures. Any questions on that there? And I think we took some time as well, talked about, again, never hurts to remind, you do want to make sure that you obviously use your exponent button if you're punching any of these into the calculator. All right, let's just do this. Let's go with how many significant figures each of these have. So take a moment and decide how many sig figs each one has. So let's take a look. So looking at the first one here, all these zeros are not significant. Again, this is where we would start counting, and that would give us 4 significant figures, including the 0 at the end, because there is a decimal place. So 4 sig figs. Coming to our second one here, starting to count right there up to 4. That is a 0 that's trapped, which is significant. So that is 1, 2, 3, 4, 5 significant figures on this guy. And again, counting here at the 1, trap 0 is significant. These 2 4s are significant. These zeros at the end are not significant because there is no decimal point written, which means that this guy would have only 4 significant figures. Any questions on that there? Now, which one is the sort of estimated digit in each of these? Again, just to remind you, not always the last one written, but the last significant figure. So that would be our estimated digit or uncertain number. That would be it. And actually for this one, it would be that digit right there where the uncertainty lies.
So, Professor.
Yeah.
And on B, when it's 43.0, how come the 0 is a significant figure? Because in the other note, it said that zeros at the beginning of decimal numbers are not significant. Is it because there's numbers before the decimal point?
Yeah, so it has to do really where, so you want to think about when you're counting significant figures, sort of, you want to make sure that you're counting once you hit the very first non-zero. So in this particular case, we hit the very first non-zero here. And that automatically tells us we're really starting to count our significant figures, which means this 3 would be significant. And when we get to this 0 is actually not a leading 0 or anything like that. It's actually a trap 0 between those 2 numbers right there, the 3 and the 2, which would make it significant. And that's different than, say, in the first one, this 0 here, these zeros that come after the decimal, these are leading zeros. We really haven't started counting until we hit the 2. So that basically what a leading 0 is pretty much all the zeros that you hit until you hit that very first non-zero number. And then once you hit that very first non-zero number, that's when you should start counting.
Okay, I understand. Thank you.
So yeah, so it really doesn't necessarily have, even though it happens to be right next to the decimal point or anything like that, we want to think about that 0 in relationship to where we started counting our significant figures. Other questions on that?
Yeah, Professor Ifan?
Yeah.
Quick question.
Yeah.
My question is regards of it's a problem with one of the homework questions.
Okay.
It is okay. So on the Pearson, there was a problem on Pearson on the beginning. It'll give me it says right here, use the correct answer from part B. Calculate the value of a rectangle prism with a length of 5.6 centimeters with a width of 2.1 centimeters and a height of 6.6 centimeters.
So I'll give you a quick answer, and I'll be happy to go over it as well in discussion if you have it today. But I think you said it asked to calculate the volume. So you basically just multiply the length times the width times the height.
And you have to round the number, right?
You do. And we're actually going to talk about how to properly round it, when you do a calculation in a few slides down the road. So if you want to wait, we'll probably maybe answer your question as to how to properly round that.
Awesome. Thank you.
No problem. Other questions on this? Okay. Yeah, so we're going to get into, again, sort of how to deal with significant figures and calculations, and obviously how to properly round something like that as well. So let's also talk about some other types of numbers. So we really are talking about measured numbers. There's also other numbers which are referred to as exact numbers. And exact numbers really come from really two sources. One is was really something that you would just count. So for example, if you had a basket of apples sitting on the table, you wouldn't do some type of weird science experiment to figure out how many apples are sitting in the thing. You would just simply go, I count it and go, I got like 8 apples or however many are there. And the other way that we get definitions, and more sort of importantly in chemistry, is they are what are referred to as these equalities. And equalities, again, are basically two values that are on different scales but represent the same amount of something. So if I say I have 1 foot, or something is 1 foot, that really is the same thing as something being 12 inches. If something weighs 1 kilogram, that's the same as something weighing 1,000 grams. Or 1 inch is 2.54 centimeters exactly. Again, that's another sort of exact number. So what is the deal really with exact numbers? Well, the deal with exact numbers are they essentially have pretty much unlimited number of significant figures. You pretty much can use as many numbers of significant figures as you want with them. What that has to do is, as we'll talk about here in just a second in terms of calculations, is we sort of ignore exact numbers when we're dealing with them in calculations. So if we come across an exact number, we sort of don't really worry about it. And again, most of the time we will see those as these sort of equalities, or they're sometimes referred to as definitions, where something equals something. Now, I will do a little side note here that we talked about kind of two different types of units, kind of the English system, which we use, the metric system. And technically speaking, when you do a metric to metric equality like that, that's considered an exact number. When you do a English to English sort of equality like this one, is considered an exact number. Now, sometimes people will say that if you go across and do like a metric to US conversion, other than 1 inch is equal to 2.54 centimeters, people will say you really should look at the significant figures when you kind of use those in calculations. I'm going to do it for us that you don't have to worry about that, but I do want to kind of tell you that, some people will tell you you do need to worry about it, and they technically are correct. But to keep it simple for us, any type of equality like we see in this table, or even, one that crosses over from metric to US, maybe like 454 grams is a pound, right? Pound is English, grams are more metric. We will still consider those exact numbers, again, with the little sort of note that some people don't consider them exact numbers, and they're actually correct. But for us, we'll consider them exact numbers. And this will make a little bit more sense as we start doing some calculations a little bit later on here in this chapter, as to where we would use them or where we would not. So if we look at these here, we see if we had 3 coins, we want to identify this as a measured or exact number. Probably that's going to be an exact number, as if you only had 3 coins, you probably would simply count it. The diameter of a circle is 7.902 centimeters. This would be a measured value, and a measured value that would then have 1, 2, 3, 4 significant figures. 60 minutes is equal to 1 hour. This is sort of an exact definition, and that would be considered an exact number. So for the most part, we come across really exact numbers with definitions. And kind of the good news is, for the most part, you don't really even have to worry about them as you're doing calculations. But they do have sort of unlimited numbers of significant figures. And let's take a look at some of these more here. So if we're looking at these guys here and we want to figure out significant figures, again, looking here, we should see that these zeros here do not count. Again, we're really not starting to count until we hit the 3. The 3 is significant. The 0 at the end is also significant, which means this guy should have 2 significant figures. Here, starting on the left, we hit a non-zero right off the bat, which means we should start counting. Now this 0 is technically now trapped between these two numbers, which makes it significant. The 5 is significant, and this 0 is significant because of the decimal point that we see in the number, and that would mean that it has 4 significant figures. All of these zeros here are going to be not significant, really, because we have not started counting. So I think we might have talked about last time that sometimes people go, well, aren't these zeros after the decimal point? And the answer is yes, they are after the decimal point, but we really haven't hit the first non-zero number to really start counting. So they are still considered leading zeros, which are not significant. And the 8 here would be significant, and this would be 1 significant figure in that case. And obviously starting here with the 2, which is our first non-zero number, would be significant. And then rolling through the rest here, the 8 significant, 0 going to be significant again because of the decimal point that's in the number. And that would give us 3 significant figures in this particular case. Any questions on any of those there? Okay, so why don't you take a second and answer these questions. Which answer contains 3 significant figures? All the zeros are significant. And for B, which one is that? And the number of significant figures in that number in C. So take a second or two, a moment, and we'll talk about it. Okay, let's take a look here and see how we're doing. I see some answers there in the chat box. So let's take a look and see. So the first one, we're looking for 3 significant figures, so might as well just go through and see what we got on each of these. So hopefully if you looked at this first number, you should come to the conclusion that it actually has 4 significant figures. Everybody there is significant. If you look at number 2 here, you should come to hopefully to the conclusion that it has 3 significant figures, starting with the 4, and everybody after it is significant. And when you look at the last number here, this is scientific notation, which means all of the numbers before the times 10 part are significant, which would be 4 significant figures. So it looks like we are looking for the 3. So that should be that guy. Any questions on that one? Taking a look at the next one, we're actually looking for all the zeros are significant in this particular case. So the one where all the zeros are significant definitely would not be this one, because this has got some leading zeros. So that guy definitely is not significant. Those zeros at the beginning has 3 significant figures, by the way. In this case, these zeros here would be significant because there is a decimal point, which means that's one of the answers, I would think. That also has 5 significant figures total. And then because all these zeros are written here in scientific notation before the times 10 part, they are all also significant. So 2 and 3 here looks like they are the correct answer for the question. Any questions on that one? Now, the number 5.8 times 5.80 times 10 to the 2. Again, this is scientific notation written, which implies that all of these numbers here are significant, which should give you 3. Any questions on counting significant figures here? All right, so more importantly, let's talk about how to do calculations that involve significant figures and how to know sort of where we should end in terms of our number, which I think was an earlier question that was sort of asked about the homework question. So really when we do, or we use a calculator, by the way, just so you know, when we do use a calculator, it doesn't always give us the answer, obviously, in the correct number of significant figures. But basically, when we do calculations, there's really kind of two operations that we use. There is multiplying and dividing. And when we multiply and divide, the answer should have the same number of significant figures as the number with the least number of sig figs. So when you multiply and divide, multiply or divide, your answer that you should end up with should be equal to the same number of significant figures as whichever value had the least number of significant figures. So for example, if I took 325 and I multiplied it by 1.2, and then I times it by 4, 6, 5, 8, 9, I am multiplying here, which means I want to look at significant figures. First number has two significant figures. I'm sorry, three significant figures. I'll learn to count. Three significant figures. Second number has two significant figures. Third number there has 5 significant figures. So when I'm all said and done and I multiply this out, my answer should end up as 2 significant figures. 2 significant figures, because really in this sort of measurements, if you will, the answer that you get or your calculation really is only as good as your worst measurement. And because this has 2 significant figures, that means that the error in this measurement basically occurs at the 0.1 spot, where over here, the error, is much better in terms of it being significant. And over here, it's way over here in terms of the sort of error that's present. So your worst measurement basically determines, sort of where you can go in terms of your answer. So if we actually multiply this on our calculator here, punching it in, I get a big old number here, like 1816971. I know I should now take it to 2 significant figures, which is here, which means I should write 180000000. I think I got the right number, 0, 0, 3, and 6. 3 and 6. Or we could use scientific notation, which would be 1.8 times 10, starting here, 1, 2, 3, 4, 5, 6, 7. And again, that would be 2 significant figures, 7. So multiplying or dividing, you want to look at significant figures. And again, is the number with the least number of significant figures is where you should kind of round your answer to. Now, we do something a little bit different if we're not doing multiplying or dividing, but if we are adding or subtracting, we look for our answer to have the same number of decimal places, not significant figures, but decimal places, as the number with the least number of decimal places. So for example, if I took 3.225 plus 1.11 plus, say, 2.0. I'll try it here without the calculator, but it looks like a 5, a 3, a 3, a 0.34, and 6. Here we are adding. So again, we're not looking at significant figures, but decimal places. First number has 3 decimal places. Second number has 2 decimal places. Last number has 1 decimal place, which means we should take it to 1 decimal place, and we should end up with 6.3. 6.3 has 1 decimal place, but it has 2 significant figures. So you want to make sure that you keep that in mind, the difference between decimal places and significant figures. So multiplying and dividing, we look at sig figs. The least number of sig figs in your calculation should be how many your answer should have. And when you add or subtract, the least number of decimal places should be what your answer should end up being. Question on that there.
Professor Ephron, can you go back?
Yeah.
That problem 3.225. Okay, that's that because I kind of got sidetracked. That's a new problem, right?
That is, so that this, are you talking about this guy up here?
Yeah.
Yeah, this guy is in what we were just talking about in terms of when you're adding or subtracting, in terms of how you should give your answer. If you add or subtract, what you want to look at is, again, decimal places and the smallest number of decimal places. So again, looking at that those three numbers that we were adding, the 2.0 has the smallest number of decimal places, only has one decimal place, and that is where we should take our answer to. Other questions?
Okay. Thank you.
Welcome. Other questions? Now, what happens if we're kind of doing, multiple math steps together, which is very common? Maybe you get an answer and then you take that answer and do a bunch of other sort of steps along the way. We do want to kind of keep track of what's going on in terms of significant figures. We don't really want to round too much usually when we're doing a sort of a long calculation until the very end. So for example, say we were doing, I don't know, a combination of both things. So let's say we were taking 3.25 plus 1.226, and then we're going to divide it by 3.2. So normally in math, what we would do, right, is we would do whatever's in parentheses first. So in terms of what's in parentheses here, we're taking 3.25 plus 1.226 gives us a number. I'll just write it next to it. If we did the top part, 4.476, and we would still be divided by 3.2. But when we're doing, technically speaking, the top part here, we are adding, which means we should be looking at decimal places. This has 2 decimal places. This has 3 decimal places, which means really if we're keeping track of where we're at, we actually should end up at 2 decimal places here, right? And that's important because technically speaking, if we did clean up this number, which I probably would not clean it up, it would be 4.48, and that now has 3 significant figures. And that's important because the next thing that we would be doing is dividing that top number by the bottom number. So we take the top number divided by the bottom number, we end up with a number of 1.39875. The last thing we just did is divide. So we took the top number, which technically should have 3 significant figures, divided by the bottom number, which has 2 significant figures. That means that our answer actually should only have 2 significant figures. We would look over here at the next number, which is a 9, and we would round up in this case, and we would end up with 1.4. That should be our correct answer. So sometimes we do really both operations together. Sometimes we do multiple steps along the way. A couple of good rules of thumb is you typically want to avoid rounding to the very end, but you definitely should keep track of all the sig figs and all that. And then at the very end, when you're done with your very last sort of calculation, you definitely should clean it up. And you should use normal rules for rounding, which obviously is if it's less than 4, you drop all the numbers. If it's more than 5, the next number, then you round up. Any questions on that part there? And that's what we were just talking about here. Again, normal rounding rules that you probably have used before. I will say that it's really important not to do what sometimes people will do, which is they really want to get the right number of sig figs. So they go a little crazy with the rounding. So for example, if we had a number such as 13,300 and 33. And we wanted to round this number to 2 significant figures. So what should it be? Well, 2 significant figures is here. Would 13 be correct? Would 13,000 be correct? So let's take a look at both of these numbers. There's probably a couple of numbers maybe that you were thinking of. When we look at significant figures, this number has 2 significant figures, so that's good. This number, the way I wrote it, has 2 significant figures. Now, they both have 2 significant figures, but one of them is not really correct and one of them is correct. So when we look at this number here that's been rounded to 13, although it does have 2 significant figures, there's a big difference between the meaning of our first number and the meaning of this number. So for example, if I owed you $13,333 and I said, hey, I'm going to pay you 2 significant figures, here's $13, we're good. Probably not good, right? There's a very big difference between $13,333 and I gave you $13. So when we're rounding and we're trying to get the right number of significant figures, it's really important to never actually change the meaning of the number. We want to try to maintain the meaning of our original number. So for example, if I owed you that $13,333 and I said, I'll give you 2 sig figs and I hand over about $13,000, you'd probably be much happier. And maybe I just get a $333 teacher discount. But the 13,333 number essentially means the same thing. So we did not change the meaning of it, and you never want to do that. But sometimes people will do that because they're so anxious, like I want to get the correct number of significant figures, which you should, that they just again sort of lough off the numbers and not realizing that they are actually changing the meaning of that number. Obviously, another way you could get to it is again writing it in scientific notation, like so. That also is 2 significant figures. Any questions on that there?
Professor Efron, if the original number 13,333 was 13,633, would you be running off to 1,400?
So you're asking if it was 13,633?
Yes.
And we're still rounding to 2 significant figures. It would then round to 14,000.
14,000, right? Okay.
Yeah. Or 1.4 times 10 to
yes. Okay, thank you.
You're welcome. Other questions? So again, try to avoid rounding to sort of the end, but again, don't go so crazy with the rounding that we do really change the meaning of it. So again, just rounding to some 3 significant figures here. I would take us to the 2. The 3 is the next number, so we just drop the rest. If we were going to 2 significant figures, we would look at the 2 and drop the rest of those. Same thing here, 3 significant figures would take us here. We would look at the 8 and round up. If we were going to only 2 significant figures, we would go to the 4 and also look at the 7 here, which would round us up to 15. And same thing here, 3 significant figures take us to 5. Next number is 6, so we would round up. And when we do round up here, we do not want to put a decimal here again because we would have too many significant figures. And if we're doing 2, we would go to here and we would round out to 3,300. Also, no decimal place, or again, you could do your scientific notation as well. All right, so let's take a look at this number here. We want to do a couple rounding here. We want to round it first to 3 significant figures. So again, we're just going to count here left to right. That's 1, 2, and 3 significant figures takes us to the 4. We then would look at the 5 and see that it is a 5. So we would round up in this particular case, and we would end up with 3.15 on that rounding up. If we were going to take it to only 2 significant figures, that would actually take us to the 1. We would then look at the next number, which is a 4, and we would basically just drop the rest of them and end up at 3.1. Any questions on that there? Okay. All right, take a second and give the answers to, looks like 3 significant figures here. So see what you come up with. Okay, so let's take a look. We want to adjust these to 3 sig figs. So starting left to right, third significant figure would be the 4. We would look at our 7 there, and we would round up 825 centimeters. Gives us 3 significant figures. We then would go left to right. We would actually start counting here at the 1, and then that's significant. That's significant. Here we would look at the 4, and we would basically drop everybody and leave it as 0.112 grams. Gives us 3 significant figures. And the last one here, this is 1 significant figure. That's 2 significant figures. We actually don't have a third one here, but we can basically remedy that by adding a 0 in there. That 0 now is a trailing 0, which is significant because of the decimal point. And now that would give us, obviously, our 3 significant figures. Any questions on any of those guys there?
Question, Professor?
Yeah.
For A, so if it would have been 825.0, that would be wrong, right?
So say it one more time,
825.0. If you added a 0.0 at the end, that would not be 3 significant figures.
Right, it would be incorrect because you would now have not 3 significant figures, but you would have 4 significant figures. So that's why we wouldn't want to put that extra 0 there in this particular question, because it wanted 3, and we just needed that part of it. Yep.
Okay, thank you.
Welcome. Other questions?
Yeah, Professor, on letter C.
Yeah.
Could you repeat why the 0 is added? Because
Zero's added, and zero's added really because of the question, because the question wanted us to take these answers to 3 significant figures.
Okay.
And this sometimes happens when you're using your calculator. For example, if you're doing a calculator, sometimes your calculator will drop that last 0 type of thing. And if you needed to report your answer to 3 significant figures, that's why we had to add the 0 in there to get us to 3 significant figures.
Okay, thank you.
You're welcome. Other questions? All right, that's that. So I kind of jumped ahead a little bit, but again, let's just review what we were just talking about in terms of answering here, in terms of calculations. So again, here we would do the top part first, really, and we're multiplying. So that's 2 significant figures. That's 4 significant figures, which means when we do the top part, we technically should have 2 significant figures that's there. We then would be dividing it by the bottom number, which technically has 3 significant figures. And that means that our answer should end up with 2 significant figures, which is what we see down here. Again, our calculator will spit us out something that looks like that. Not always the correct number of significant figures given to us, but we do want to kind of follow through our calculation and keep track of our significant figures when we're doing it. Same thing here. We're dividing. So we are looking at significant figures. The top number has got your 3 significant figures. Bottom number also has your 3 significant figures. Again, as was sort of the question just a second ago, this is again very common. Your calculator may just give you a 4, which obviously is not the correct number of significant figures. If you just reported 4, it would have 1 significant figure. But we know from what we've been talking about that we do need actually 3 significant figures. So you yourself would have to add those extra couple of zeros there to report your answer to the proper number of significant figures. So again, it's a very common thing that sometimes happens, you know, when you punch it into your calculator, it just spits you out an answer sometimes. And again, maybe you're right on sig figs. Sometimes you get lucky, but most of the time the answer that your calculator gives you is probably not the correct number of significant figures. So sometimes you do have to sort of adjust it to get yourself there to the right number. So let's take a look at this one here. Again, we would normally perform the top part first. So we are multiplying here. So we're basically taking 5 times 3.408. Here, that would give me an answer up on top of 17.04. Now, personally, if I got that number in my calculator, I would keep the whole number. But what I would want to do is look at what I just did and go, okay, I'm multiplying. So the 5 has 3 significant figures. The 3.408 has 4 significant figures. So technically speaking, the top number really should end up at 0. And that's important because then I'm going to take the top number and divide it by the bottom number, which is going to give me an answer of 8.52. Now, that's important because technically speaking, the top number should be 3 significant figures. I just divided it by the bottom number, which has 2 significant figures, which means my answer should end up with 2 significant figures. And that means my answer should end up right there at the 5. And it should really be 8.5 centimeters. So again, personally, I would not round, but I would definitely keep track of where the significant figures are as you go through these different parts of the calculation. And then again, clean it up at the end like I just did there. Any questions on that particular one?
So Professor, on that one, you divided before you run it off?
Yeah, I personally do. It's just good practice. Because when you round, for example, and say you're doing multiple steps in a problem, like you do one step, you get an answer, you take it, do another calculation, get an answer, take it, do another one, and so forth. Every time you sort of round after each little step, you're probably moving yourself further and further away from the actual correct answer. So it's really sort of good practice to kind of really avoid rounding or a lot of rounding until you get to the very end. But you definitely should keep track of it like I did here, even though I kept like the, where did the thing go? Even though I kept the whole number, I know that technically speaking, the top number really should only go to there, which is 3 significant figures, which helped me when I did my division, that's 2 significant figures that helped me clean it up at the end. And that's usually fairly good practice when you're doing calculations to really not round a lot, take everything to a couple of extra digits, and then sort of clean it up there at the end to the right number of significant figures. But to answer your question, yeah, that's exactly what I did with my calculator. I just took the 17.04 number and I divided by 2. Now, clearly, if you did some rounding here and then divided it, you may end up with a slightly different answer. And in most cases, you'll probably be okay. But the normal rule is to really try not to round too much until kind of the very end.
Okay. So you would only run off if the numbers were really large?
Yeah, no, look, if you, and there's a couple of different ways, I guess, of saying this are practicing it. So if you have a giant number, right, and you don't necessarily have to write the giant number. So for example, say it was a big number, but maybe take it to just a few extra digits. Like normally, if you were supposed to round to here, maybe take a couple of extra digits if you're going to write it. But in your calculator, you can leave the whole number, and do the next part of the calculation. But you don't necessarily have to write it. There's like 400 digits. You can figure out, okay, my answer should be maybe to the 3rd significant figure. I'll keep a couple of extra. And that's usually a good way of doing it. Yeah. So you don't necessarily have to write every single digit all the way around the page or anything like that. But usually keep a couple of extra digits past where you should have rounded and then continue on with the calculation. And that usually will put you, when you're all said and done, pretty close to what the true answer really should be. Other questions on that?
Professor?
Yeah.
So what happens if the numerator isn't like an addition problem? So what if it was 5.00 plus 3.48 divided by 2.0?
Yeah, so you would do it very similar to sort of that other example I think we did. You would just do the same sort of operation. So like 5.00 plus the 3.408, and then we'll divide it by the 2.0. So you just do the addition part first. And for example, we do 5 plus 3.408. Technically speaking, here you would get an answer of 8.408 on your calculator. Here we would be looking at decimal places, which would be 2 and 3. And again, our answer really should go to 2 decimal places. So again, here I would just make a little note to yourself or keep in your head and go, really, this is where that top number really should end. And I personally, again, would probably keep all the numbers there and then divide it by 2. And that would give us an answer of 4.204. Now, when we know that we should end here at that 0, that basically means that this guy now has 3 significant figures divided by the bottom number that has 2 significant figures, which again would take us to here. And our answer would be, in that case, 4.2.
All right, thank you.
Yep. So again, you just want to really kind of keep track of it. And sometimes people teach students to put like a little line over where, technically speaking, if you rounded strictly following the rules, that's where you should round. But again, just general practice, like I was mentioning earlier, if you figure, okay, I should stop at the 0 and you only got one other number, keep the number. If you just stop at 0 and you got like 5 or 7 more numbers, maybe keep a couple of the numbers past it and then continue on with the calculation. And again, usually you'll be in pretty good shape when it's all said and done. Other questions on that? Okay. So there's that. By the way, you should include the units as well. We talked about obviously adding as well. So again, here we're adding. Sometimes people get a little confused. Again, we're not looking at significant figures here, but we're simply looking at decimal places. So as we mentioned before, this guy would have 3. This guy has 2 decimal places. This guy has 1. So we would want to round it off to 1 decimal place. But if we were then going to take this number, kind of like we've been talking about, and continue on with another calculation that has 1 decimal place, but for the sake of argument, if we needed to do sig figs, that number now would have obviously 3 significant figures. So sometimes people get a little confused on the decimal place, sig fig type of thing. But remember, when you're adding or subtracting, go to decimal places, but that most likely will give you a number that has a different number of significant figures, which you might need to use as you continue on with the calculation. So same thing here for subtracting. Also, we see the 3.0 goes to 1 decimal place, which means that we should round up in this case to our 62.1. Again, has 1 decimal place, but 3 significant figures if we needed 3 significant figures along the way. Here we are adding. So again, looking at decimal places, 3 decimal places, 1 decimal place. So if we put it together here, we would go to 1 decimal place. Next number is a 0, which means we just round or drop it, and we end up here at 1 decimal place. Again, if we were to continue on with sort of this calculation, this guy would then have 4 significant figures if we needed to look at significant figures, if we were doing some type of multiplication along the way there. Any questions on that there? Okay. Questions on calculations involving significant figures. Obviously, you should always give your answers to the proper number of significant figures. And again, you just want to kind of keep track of them as you're doing the calculations. Try not to round too much to the very end, and then sort of put them together. All right, the next thing we're going to talk about is sort of prefixes and equalities. We're sort of moving into sort of conversions and doing conversions here. So a prefix is, as we will see, something that we use to really change the meaning of a number. So very large number and very small numbers. We use a lot of prefixes in the metric system like kilo, milli, centi, and so forth. An equality is, as I think I might have mentioned before, basically 2 values that are on different scales, but do represent the same amount of something. So clearly this is an equality here. If you have 100 pennies, that is the same amount of money if you had $1. You could pay in pennies, right? You could pay in dollar bills. Although if you pay in pennies in a drive-through, they may not let you through. But, it really is the same amount of money. And that's basically what an equality is. And as we'll talk about, pretty much from any equality, you could write conversion factors. And what are conversion factors, as we will see a little bit later on here, they're basically just fractions. You could say like in 100 pennies, I have $1. Or you could say $1, there's 100 pennies. And we use these really, as we'll talk about a little bit later on here in this chapter, doing what's referred to as dimensional analysis, to go from basically one unit that we're not interested in to another unit that we are interested in. So let's talk a little bit about prefixes. Prefixes are, again, really used in the metric system to change the meaning. And for example, 1 kilometer equals 1,000 meters. So sometimes when we talk about sort of a prefix, there's sort of a relationship of what is sometimes referred to as the base unit versus the prefix unit. And what I mean by that is when we look at, say, something like this, kilometer and meter, the base unit here is the meter. The prefix unit is the kilometer. So there's always sort of a base unit, for example, milliliters and liters. Liters is the base unit, milliliters is the prefix unit. We could write a conversion factor like this. Again, this has 1 kilometer over 1,000 meters. Or we could say 1,000 meters over a kilometer. And as we will see, we could use these conversion factors to convert something. You know, if we had 5 kilometers and we want to know how many meters that was, we could do a little math. This is what is referred to as dimensional analysis. We could do 1 kilometer is 1,000 meters. So we're clear of what we're doing here, although this is not written as a fraction, it's kind of like a fraction. Opposite units in terms of their locations cancel because we're multiplying across the top and dividing by the bottom, which basically means we're dividing kilometers divided by kilometers equals 1. Just like when you divide 2 by 2, it equals 1. If you divide kilometers on top divided by kilometers on the bottom equals 1. We then would take 5 times 1,000 and divide it by 1. And that would give us 5,000 meters in 5 kilometers. So this is commonly what we use sort of the conversion factors for. And again, we could use these prefixes to sort of change the meaning of a metric number. The prefix, it doesn't really matter the actual base unit because it's the same sort of relationship. So as I was mentioning earlier, in this case, the base unit is meters and 1 kilometer is 1,000 meters. If I change the base unit to liters, 1 kiloliter is 1,000 liters. And if I change the base unit to grams, 1 kilograms is 1,000. The take-home message here from all these is when you say kilo, you're talking about basically 1,000. And it doesn't matter really what the unit is, meters, liters, grams. If you have a kilo of something, it's basically 1,000 of it. And again, we can use those, you know, depending on the unit or the quantity of the unit. Now, let's talk really about a very common sort of table that you will see in most textbooks, and this does come out of your textbook, I believe. And, you know, a lot of times people will look up, you know, and they have to do a conversion. Say they want to do mega, for example. And they look up mega and it says 10 to the 6. And it's very common that people will always do this conversion incorrectly. So when you look at a table such as this and you see it say mega is 10 to the 6, kilo is 10 to the 3. By the way, that's scientific notation, which basically means 1 times 10 to the 6 or 1 times 10 to the 3. But what that means is that is how much there is in the base unit to one of the prefix units. So if we took mega, for example, mega on the table, there's 10 to the 6, which means if I had 1 megagram, that would be 10 to the 6 grams. Again, base unit here is grams. prefix unit is here, and one of the prefix units, there's 10 to the 6 grams. If I had 1 megaliter, that would be 10 to the 6 liters. Again, prefix unit, base unit, and it's very common people will kind of move it and do it reverse. So for example, if we look up kilo, 10 to the 3. In 1 kilogram, there would be 10 to the 3 grams. And it's very common that people will write this backwards, like there is 10 to the 3 kilograms in 1 gram, and that is incorrect. So whenever you look at a table such as this, and I think it continues to the next page, and you see these kind of scientific notation of what the prefixes is, that is how much there is in the base unit to one of the prefix units. So again, if we looked up centi, it is 10 to the minus 2, which means in 1 centimeter, there is 10 to the minus 2 meters. Again, that's how much in the base unit there is to one of the prefix units. Question on that. And again, that's a very common error that people make, is they always do the conversion backwards. They like flip it around and do it incorrectly. Any questions on that one there? Yeah. And by the way, if you needed to punch it into your calculator, like 10 to the minus 2 or whatever it may be, you can punch it in scientific notation like we talked about. You would go 1, your exponent button minus 2. It's a good way of doing it. And depending on your calculator, you might even be able to put exponent button minus 2. You will be coming across these prefixes often. So in terms of common ones that we do see probably in this class, I would say centi comes up a lot. Milli definitely comes up a lot. I don't know too much on those bottom ones. Kilo comes up a lot. Maybe deci as well. Not too much micro, not too much nano or picometers in here, but I would say those kind of 3 or 4 we will see a lot. So you do need to be able to use them obviously correctly. You should have some familiarity with it, but again, you may be provided, something that looks like this, like, hey, centi is 10 to the minus 2. You need to be able to use that as like a conversion factor sort of correctly. Other questions? Okay, so we'll skip that there. Let's take a look here. 1,000 meters is 1 kilometer. 10 to the minus 6 grams is equal to, that's actually microgram, which is that sort of symbol, micro, kilo, micro. And 0.1 liter is equal to 1 deciliter there as well. Now, you may be wondering, well, like centi is 10 to the minus 2, right? And again, what that would mean is 1 centimeter is 10 to the minus 2 meters. You may also have learned 100 centimeters is 1 meter. And that's kind of what you get when you divide 10 to the minus 2 to both sides. So if you take 1 centimeter is 10 to the minus 2 meters, and you divide 10 to the minus 2 on both sides, that becomes 1 meter. If you divide 10 to the minus 2, 1 divided by 10 to the minus 2, you get your 100 centimeters. So they're the same conversion. Sometimes you'll see it like this. Sometimes you'll see it like this. And again, dividing it to the other side is how we get to those sort of conversions. Okay, so we did kilo there. So some very common equalities for length that we do use a lot. 1 meter is 100 centimeters. We comes across a lot. 1 meter is 1,000 millimeters. Now, if you're going from, for example, one prefix unit to another, it is sometimes best to, so for example, if you want to go say centimeters to kilometers, right? Sometimes people try to figure out how many decimal places should I move, or I think there's even a song that has how do you do it as you go from one to the next. But in terms of doing sort of the conversions, it's a good idea to take it from the first prefix unit. So for example, 1 centimeter, and there are 100 centimeters in 1 meter. And if we do that, that then takes us to meters. And then you could easily find the conversion for kilo, which is 1,000, and take it from meters to kilometers. So I highly recommend that if you're sort of doing a prefix to prefix conversion, because you could really find those kind of conversions on a table like this, take it to the base unit first, because you could find that, and then take it from the base unit to the next prefix unit, and you'll usually get it correct. Sometimes people try to do it all together or move the decimal place, and usually ends up with the wrong sort of answer. And by the way, when we look at a ruler, right, up on top are typically inches, on the bottom, big numbers are centimeters, smaller numbers are millimeters. There's 10 millimeters and a centimeter. So if you look at a ruler, there's 10 little markings to hit the one big guy on the bottom, and that would be 1 centimeter. So centimeters, millimeters, kilometers are common sort of length measurements that we do come across a lot. All right. Now let's talk a little bit about volume. Volume is basically the three-dimensional sort of property there. And there's a couple different ways we could get volumes, but some common ones are here. 1 liter is 1,000 milliliters, which is something that we use a lot. Again, you could write 2 conversion factors. 1 liter is 1,000 milliliters, or 1,000 milliliters is 1 liter. And one common way that we can take a volume or get a volume is, as we talked about when we're talking about taking a measurement, is to simply fill up a glassware, read the volume from the bottom of the meniscus. Another common way that we could get it is, especially with a solid, and sort of like I think there was an earlier question that was asked, is we can actually take 3 different length measurements. So we could take the length cube basically by taking the length times the width times the height. And each of these are length measurements, which, for example, if we measured each of them in centimeters, centimeters times centimeters times centimeters gives us a cubic centimeter. A cubic centimeter is actually a volume. Each of these individual measurements here are length measurements. So basically, if you take length and you cube it in a cube type situation, that will give you a volume. So I think their other question was about, they give you 3 sort of length measurements in that homework problem. You would want to multiply them all together, and that will turn it into a volume. And obviously now we talked about the sort of rules for significant figures. You would round it accordingly. Now, a cubic centimeter is the same thing as a milliliter. They are a 1-to-1 conversion. So that's a really good thing to know. And in medicine, sometimes they use cc for cubic centimeter. I give somebody 5 cc's of something, right? And as we will see here, I think on the next slide, 1 cc, again, it's basically 1 milliliter when we're looking at a syringe. And that's a cubic centimeter, same as a cubic centimeter in like this, or 1 milliliter here. So a volume, again, is basically the amount of space that's occupied by a substance. And again, those are 2 common ways that we get the volume of something. Simply fill it up and take a reading, or again, do like a length times width times height type of measurement. Any questions on that there? Now, in terms of mass, there's also some very common ones that we come across in terms of quality. 1 kilogram is 1,000 grams. That is definitely something we see a lot. Also, this one, 1 gram is 1,000 milligrams. Those are two very common ones. Again, if we wanted conversion factors, 1 kilogram over 1,000 grams, or 1,000 grams over a kilogram. Again, if we said, hey, we were, 444 grams, how many kilograms that would be? We want to go opposite in terms of units, so we would use the conversion factor over here. This would be 1,000 grams. This would be 1 kilogram. And again, dividing grams by grams will cancel out those units. Math-wise, what we're doing here is 444 times the top number, which is 1, hit equals. We're going to divide by the bottom number, which is 1,000 in this case. This gives us 0.444 kilograms. So when we do a calculation like this, we do want to follow our significant figure rules. So earlier, if you remember, we talked about the idea of exact numbers. And exact numbers are numbers, right, that are counted or definitions. And when we do calculations that involve exact numbers, we pretty much ignore them in terms of the significant figures, which means when we look at this calculation, this is considered an exact number, which means we really don't even look at it when we're trying to determine how many significant figures our answer should have. So that means that we come back to really our original number here, which has 3 significant figures. And that means that when we're done, our answer should also have 3 significant figures. So if you're doing some type of conversion, like kind of this problem is, for the most part, the number that you get at the end probably should have very similar number of significant figures as your original number. That usually is a pretty good case, like in terms of what will end up. Any questions on that there? Yeah. So which one is the larger unit here? Millimeters or centimeters? The larger unit here is a centimeter. Centimeter is larger than a millimeter. Again, the millimeters are the smaller lines on the ruler. Millimeters are bigger lines. In terms of a kilogram, kilo is larger than centi. Kilo is 10 to the 3. Centi is 10 to the minus 2. So kilogram here would be larger. Deciliters and microliters. Deciliters is larger. Micro just sounds smaller, and it is. In terms of that, one is 10 to the minus 1, and one is basically 10 to the minus 6. And here we have that is milligrams or micrograms. So that's what that is. That's micrograms, basically. Micro symbol is that little kind of U looking thing. It's not really U, but micrograms is smaller. Milli is basically 10 to the minus 3, much smaller than micro, which is a smaller value. All right, here, some of these we've sort of touched upon. 1,000 meters is a kilometer. And that's basically what kilo kind of stands for, 1,000. 0.01 meters, which is basically 1 and 2 places this way, if you're not sure, that's 10 to the minus 2. And 10 to the minus 2 is centis prefix. And that would be 1 centimeter in this particular case. Any questions on those two? Yeah, question?
Yeah, Professor Ifan, I actually was about to ask you a question and this slipped out of my mind right now. It was about, it's a little off topic, but it's to the class. How do you differentiate the difference between mass and weight?
So there is a difference between mass and weight. So mass is independent of the force of gravity, while weight is dependent basically on the force of gravity. So for example, when you if you weigh yourself here or you weigh yourself on the moon, if you happen to get to the moon, you would weigh differently because the force of gravity here versus the moon is different. But your mass would be the same because mass is independent of the force of gravity. So in chemistry, when we do weigh something, we do refer to it as getting the mass of the object. We do not usually refer to it as getting the weight of the object, again, because weight basically takes into account the force of gravity.
Okay, got it. Thank you.
Yep. Other questions? So 1 kilogram is 1,000 grams. So there's our kilo again. And we got our 0.01. I think this actually should be 1. I think they gave the answer in the question. I think that should be 1 centiliter is 0.01 liters in that case. So that's what that one should be, I think. All right, so we sort of talked a little bit up to this point about really writing conversion factors as I was doing that just a second ago. But we do use conversion factors really to go from sort of one unit to the next. And it's really used, as we will talk about, in a process that's referred to as dimensional analysis. And dimensional analysis is a fancy word for really conversion factor problems. And the idea behind sort of dimensional analysis and using inequalities and conversion factors is, for example, if you have, say, unit A equals unit B, for example, and you were starting with unit A, whatever that unit may be, and you want to get rid of it and get yourself to the other unit, we could use this equality and write 2 conversion factors, unit A over unit B, and it's really just a fraction, numerator and denominator. Or we could write unit B divided by unit A. Maybe I'll write down here, unit B and unit A. You can actually see it maybe. So when we have a conversion factor, we never will use really both of them together because you'll undo it. But as we sort of talked about a couple of those little examples we did just a minute ago, when we look at this, this is not really written as a fraction, but we can sort of think of it as a fraction, like a numerator and denominator, top and bottom. And when we're trying to cancel out units, as I mentioned before, we want to do opposites cancel the units. So if I were to try to use my conversion factor here, I would definitely want to use this conversion factor because units A is on top. So to get rid of it, I need to put it on the bottom. And the unit I want will go up on top. And again, mathematically, what we would be doing is taking unit A times unit B and dividing it by unit A. So when we divide, unit A on top and unit A on the bottom will cancel, as I mentioned before, like when you divide 2 divided by 2. And the only unit that will be left is unit B. And this again is what is referred to as sort of dimensional analysis using conversion factors to really convert from one unit to the next. And I guess we will pick that up in a week, right? Because Monday, I believe, is a holiday, if I'm not mistaken. So there shouldn't be class on Monday. So we'll pick this back up on Wednesday. A couple of things before